right, in this podcast, we're going to talk about electrons and light. So there's this dilemma of the atom that electrons are outside the nucleus. They're attracted, they're negatively charged. They're attracted to the protons, which are positively charged in the nucleus. We have charged particles, though, that are moving in a curved path. So based on what we know about physics, we know that they should be losing energy and will eventually crash into the nucleus. So what keeps the atom from collapsing? Okay, so J.J. Thomson and George Thomson both won the Nobel Prize for saying different things. One of them says the electron is a particle. The other one says the electron is a wave, an energy wave, a wave of energy. Okay, so who's right here? They're both right, okay? So electrons have what we called wave-particle duality. So we have to understand both properties of waves and particles to be able to understand electrons better. We know, everything we know about the structure of atoms has arose from the studies of interaction of light with matter. All right, so we know that electromagnetic radiation or light basically is going to move through a vacuum, which means there's no molecules, with a speed of 3 × 10⁸ meters per second. We also know that electromagnetic waves have characteristic wavelengths and frequencies. So here's a big picture of the whole entire electromagnetic spectrum. Notice this little center area here. That is where the visible spectrum is. This is the part that we can actually see. This is everything else, okay? So this is radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays, okay? So notice that they all have characteristics, wavelengths, and frequencies, okay? So wavelengths and frequencies. What the heck are wavelengths and frequencies? Wavelength is the distance from the crest to the crest, okay? So we call the top of the wave the crest and the bottom the trough. So the distance from the crest to the crest is called the wavelength. We measure that in meters, nanometers, and angstroms. You'll mostly see meters and nanometers. All right. Frequency is basically the number of waves that pass a given point for a unit of time. Okay, so essentially, like if this is a characteristic time, like maybe say this is 1 second right here. All right, so this one, all of this is going on in 1 second, and this one, you see that you have a longer wavelength, which means you have a lower frequency. Okay, so the wavelength, so from crest to crest, is longer. Therefore, you have less waves that are passing, going through this same section in the same amount of time, okay? All right, so that kind of leads us to this equation that says that the speed of light, c, is equal to the frequency times the wavelength. Wavelength is going to be this crazy little lambda, and its units are meters. And then frequency, the unit is 1/seconds. All right, so if we were going to try to solve a problem with that, we have a photon of red light has a wavelength of 665 nanometers. What is the frequency of this light? All right, so you're basically wanting to take the information that, so you know your equation is this. Sorry, I put it on highlighter. Not really sure why. There we go. All right, so there's our equation, and we know this is our wavelength, right? So what's wrong with our wavelength here? Hopefully you notice that it's in nanometers. So you are expected to know that 1 nanometer is 10⁹ of a meter. Okay, so you're kind of expected to know that. So if I were to go over here and start plugging in stuff, so I know C's a constant. It's 8 × 10⁸. Just kidding. see, I mess up too. It's not 8, it's 3, right? Okay. Glad y'all caught me on that one. Haha. All right, so it's 3 times 10 to the 8 meter per second. And then our wavelength is 665 times 10 to the negative 9th meters. And then we're trying to find the frequency, which is V. So we do a little algebra. So we're going to divide by this on both sides. So basically bringing this over here, dividing. And we arrive at our answer, which tells us that frequency is 4.51 times 10 to the 14th. And then remember that the unit for frequency is hertz or 1/seconds. Either one of those is acceptable. So that's basically how you would solve that problem. All right, here's a different one. This time we're given the frequency. So that's our frequency. It wants to know what the wavelength is. So we have the same equation. And we're going to try this time to solve for wavelength. Okay, so we've got our C, which is always the same, 3 times 10 to the 8th, equals, looking for the wavelength this time. So that's our unknown. And then our frequency is 7.25 times 10 to the 20th hertz, or you can put 1/seconds, whichever. Now again, do a little algebra. So we're going to divide by this number right here on both sides. So basically that gets divided over here, and you arrive at your answer, which is 4.14 times 10 to the negative 13th of a meter. So that's our wavelength for an X-ray. Okay? All right, so along with that, Einstein started looking at the energy of electromagnetic radiation, and he said that light travels in these little packets called photons. And the energy of a photon is equal to H times V. So H here is our constant in this equation, meaning that it never changes. So it's 6.63 times 10 to the negative 34th joules per second. And E are going to be our energy of our photon in joules. And then we still have our frequency, which we also had in the previous equation, which is 1/seconds. All right, so looking at this equation, we can determine some more things. So it says that a photon of red light has a wavelength of 665 nanometers. What's the energy? Okay, so this one, we know that we have two equations, right? We have C equals lambda V, and we have E equals HV. Okay, well, this is our wavelength, and we're trying to get to our energy. Okay, so we're going to have to use both equations. We're going to use the C equals lambda V first. So we know that C is 3 times 10 to the 8th, and that is equal to our lambda, which is 665. And remember, nanometers is times 10 to the negative 9th meters. And then we're looking for our frequency, our V. All right, so again, doing a little algebra, so dividing, getting this over here, getting our frequency by itself. We already solved this earlier, so this answer should not look foreign to you. But this was the frequency that we got. Okay, all right, now we can plug that into our next equation to solve for E. So we have E equals HV. H is our constant, which is 6.63 times 10 to the negative 34th. And then our V, which is 4.51 times 10 to the 14th. And that's going to give us our energy. All right, which this is a lot simpler algebra. You just multiply. So the energy of a red photon of red light is 2.99 times 10 to the 19th. That's a negative 19th, my bad, joules. All right, so this one, we have an X-ray has a frequency of this. What is its energy? So again, you have two equations. Okay, all right, so we already know the frequency, which is our V, and we know our H, so we can go straight to this second equation. Okay, so we're going to plug in our H, which is the 6.63 times 10 to the negative 34th, and then our frequency, which is 7.25 times 10 to the 20th. Okay, so 7.25 times 10 to the 20th multiplied by the 6.63 will give us our energy of an X-ray photon, which is 4.81 times 10 to the negative 13th joules.